Okay, guys, so we're going to continue with Gibbs free energy. This is the formula that we were using before. So I just want to emphasize a couple of things, okay? So remember that when Gibbs free energy is negative, we have a spontaneous reaction. Spontaneous means that it goes forward without any influence from the environment. So this is going to be a favorable reaction. This is the word that they use in College Board, right? So it is a chemically favorable reaction. When delta G is positive, or the Gibbs free energy is positive, that is going to be a non-spontaneous reaction, right? So non-spontaneous, remember, means that it's not chemically favored. It is going to not proceed forward unless it has an outside influence, and this is non-favorable reaction. So I wanted to make sure that I included these in your notes because this is the language that they're going to use on the exam. They're not going to use spontaneous or non-spontaneous, or they may, but they're also going to use favorable and non-favorable, okay? Now, if a reaction is favorable or spontaneous, right, then this reaction is going to favor the products. So this is going to go toward the products, right? Because remember, a spontaneous reaction is going to be a reaction that moves forward to completion without outside influence. So this is going to favor the products. If a reaction is non-spontaneous, that means that it's not going to move forward unless it has that outside influence. So this reaction is going to move in this direction towards the reactants, right? Towards the reactants. So you're going to see questions like that. Does this reaction favor the products or the reactants? And you basically just got to take a look and see where the delta G lies, or the Gibbs free energy, okay? Now, when we're talking about Gibbs free energy, okay, these guys are going to be the big players. It's going to be your enthalpy and your entropy, okay? And you're going to see questions that are going to ask you questions like, based on this enthalpy or based on this entropy, is this going to be a favorable or non-favorable reaction? So if this one is bigger, right, a bigger value, which means it's going to have a positive entropy, right? And this is a small value, right? Then it's going to make delta G negative, right? It's going to make delta G negative. And we talked about this up here. I give you guys a little table, all right? So just know that when both of these are small, the enthalpy and the entropy, that's when you start looking at temperature, okay? So when you have these questions like this, you just gotta think about it for a minute, right? Because it's gonna depend, whether or not the overall sum of the reaction is gonna end up with a negative or a positive delta G, because you're gonna get a lot of questions that are gonna ask you to infer stuff like that. So just be mindful of that, okay? Now, what happens when delta G is equal to 0? When delta G is equal to 0, what's happening here is the reaction is not moving forward, it's not moving backwards, right? And what's happening here is that this is now at equilibrium. The reaction has reached equilibrium. So in the instance where you see that delta G is equal to 0, right, then that's when you know that your reaction has hit equilibrium and it's not moving in either direction, okay? Now, when delta G is equal to 0, right, then what's happening here is your delta H minus your T delta S is now going to be equal to 0, right? So what does that mean? Well, that means that if you have a delta G that's equal to 0, then you have a couple of assumptions you can make. So for example, you can say that delta H is then equal to T delta S, right? Or you can solve for delta S and understand that delta S is equal to delta H divided by T, right? And then lastly, you can see that temperature would equal delta H divided by delta S, right? So at equilibrium, right, you can use the formula and you can determine unknown values depending on what you're given, right? And then solve for the others, because remember, now you're setting everything equal to G. All right? Okay, I'm going to try and keep this one short, so we're going to go ahead and move on. Now, when we start working with equilibrium, that's when we start introducing equilibrium constants, right? Remember that equilibrium constant is equal to the K, and when we're working with Gibbs free energy, then that formula takes on a whole new look. Right? So delta G in this case is equal to the gas constant, right? Which is R. R, remember, is equal to 8.314, right? And this is going to be moles K, right? And the natural log of whatever your equilibrium constant is, right? So this formula is going to be in your formula sheet, and I'm going to go over just a quick few examples of how we use this formula. So let's say we have a reaction that is 2NO gas plus O2 gas is now at equilibrium, right? To produce 2 moles of nitrogen dioxide gas. Okay. You also want to pay attention, right? Because you're going to get questions that are going to ask you about entropy, right? And you got to take a look at the states. Now, in this case, you're not going to see much change in terms of the state of matter, but like if you're going from a solid to a liquid or a liquid to a gas, you're going to definitely see an increase in entropy. If you see bonds breaking, right, and you have more than one molecule on the product side, then you're definitely increasing the level of disorder. So that's going to see an increase in entropy, and exactly the reverse is true. So also pay attention to your states of matter and your number of moles, because you're going to see questions that are going to ask you regarding entropy. And remember that entropy is the increase of disorder in a system. So it says here, let's say we have a value of Kp, right, that has a value of 1.7 times 10 to the 12, right? And this is going to be at 25 degrees, right, Celsius. Okay. I want to know what is my delta G at this reaction, right? So what do we do, right? What do we do? So what we do is we take a look at our formula, which is delta G is equal to RT ln times the Kp. The Kp can be Kp, it can be Kc, it can be whatever it is. Just know that it's going to be your equilibrium constant, right? Okay, so what we're going to do here is we're going to substitute our gas constant, which in this case is going to be 8.314, right, moles Kelvin. Right, we're going to switch gas to Kelvin, which in this is going to be 298.2 Kelvin. Okay, and then we're going to put in our Kp, right? We're going to multiply by the ln of Kp, which in this case is 1.7 times 10 to the 12. Okay, all right. Once we have that set up, all we got to do is simplify, right? If you multiply all this out, right? The natural log of 1.7 times 10 to the negative 2, right? That's going to give you 28.6, right? So that's 8.314 times 298.2 times 28.16. All right. And if we simplify this further, we're going to get negative 6.982 times 10 to the 4 joules, right? And then if we want it in kilojoules, it's just going to be negative 69.82 kilojoules, right? Kelvin cancels here, right? Kilojoules. Okay. Sorry guys, kind of rushing. It's joules per mole. Remember that this is in joules per mole. Okay. And then your joules are going to cancel here. And then your moles are going to cancel here. All right, joules, moles. Okay. So that's pretty much it, guys. Let me give you one more example, and then we'll cut this video short here. Let's say we have a reaction now that says we have 3SO2, right, gas, plus O2 gas is again at equilibrium, right, to produce 2 moles of SO3 gas. Okay, now in this situation, right, for the reaction, we know the delta G. The delta G is given at negative 33.4 kilocalories. All right, this is going to be at 25 degrees Celsius, right, and it's asking for the value of Kp. So in this case, the Kp is the unknown, right? So it's going to be the same thing. We're going to use the same formula. Delta G, right? Again, delta G is equal to 33.3, right, minus RT ln times the Kp. All right. So what we're going to do is we're going to solve this equation for Kp, right? So let's go ahead and divide then by RT. All right, that's going to give us the ln of Kp is equal to the delta G divided by the negative RT. All right, with me so far? All right. Now, in this case, the delta G is equal to negative 33.3 or 4, right? We're going to divide that by the RT, which is 8.314 times 298.2 K, right? Now, if we write this out in units, right, this is going to be negative 33.4 kilocalories, 8.314 joules per moles K, times 298.2 K. Okay, so take a second, pause it, and to see if there's something that we did wrong here. Did you see it? Okay, so take a look. This one is expressed in joules, and this one is expressed in calories. Okay, that's not going to cancel, guys. So because that's not going to cancel, we need to use another value for R. R is also equal to 1.987 calories per moles K. Obviously, you're not going to need to remember this because if they give it to you like this, it's going to either be in your formula chart or it'll be directly in the question. So now we need to rewrite this as 33.3, right, or 33,400, right? This is going to be in calories. Okay. Did it again. Here we go. One 1.987, right, calories per moles K times 298.2 K. Okay, calories are going to cancel. See, Kelvin's going to cancel, right? And then your moles should be here. Those should cancel also. All right. Now, let's go ahead and simplify this. This is all equal to ln of Kp. All right. If I simplify this further, I'm going to get the ln of Kp is equal to 56.4. All right. If I want to cancel the ln, I'm going to raise both to the power of e. So then Kp is equal to 3.0 times 10 to the 24th. Okay, so that's the value of the Kp. You may not be asked to do this, but at least you know that you're going to have to work with your natural logs. Make sure to pay attention to your units. And that's going to be pretty much the gist of the Gibbs free energy. Pay special attention to the values of your H and your S. And remember the terms favorable versus non-favorable. Remember that favorable favors the products, non-favorable stays at the reactants. And just manipulating this formula here, okay, is going to help you answer a lot of the questions as long as you understand that delta H is equal to energy, right, or heat. And the delta S is your entropy, right? Entropy or disorder. Okay, so just remember that and just manipulate the equations. Okay, that's it for today.